Hello and welcome to this video entitled Rational Equation Applications. We are going to be looking at two different ways we can use rational equations or equations with any kind of rational expressions built in or fractions built in to represent some real world ideas. To start with, we need to talk about something called velocity. It is what you call additive, meaning that if you were to take a car and drive it 60 miles an hour, and then you attach a rocket to it that shoots at 300 miles per hour, to find your final velocity of this object, like the car we're talking about here, you would have the 300 miles per hour plus the 60 miles per hour for the car. And then at the end, this rocket car would be going at 360 miles per hour, for example. And I will link some other videos that kind of deal with the situation related to what we're doing today in our assignment, and you guys can check that out if you'd like. Now, the two varieties of applications of expressions are most commonly referred to as work problems, where you have two or more people working together to complete one task, or you have motion problems, which are mainly dealing with the physics formula of distance over time equaling your rate, similar to the velocity thing we talked about before, where that is miles over hours equals your speed or velocity. So the first type is work problems. So if we kind of look at what we have going on in this page here, the most important thing to note is that we're going to have each of these first two parts that I've kind of circled in yellow here. These parts here are going to end up being fractions. You're going to do a certain fraction of the job per hour or per however many per hour, and then you multiply by how many hours you're going to work together, and the two people will finish one whole task in that amount of time. And remember, this could be two or more people. When it's two or more people, you just have more than two fractions as part of their each individual rates. And then the example we have, if we have this person, Carla, and they can complete a task in 4 hours, well, they would have completed 1/4 of the task in 1 hour. So her rate is basically a quarter of the task per hour. And so if you have more than 1 hour, you would have a quarter of the task times however many hours that Carla is working. So continuing onwards, we can continue into our next slide here. So now on our example here, we have Carla from before and Josie both work for a legal data storage company. Working alone, Carla can type a 34-page legal document in 4 hours. So she's completing, we're going to ignore the 34 here. That's not really that important for our purposes. We're really going to focus on she can do it entirely by herself in 4 hours. You compare that to her friend Josie working alone. She can do that same document in 6 hours. So if you think about like their different individual rates, what Carla is kind of doing in 4 hours, so she's kind of doing one job in 4 hours. So that would kind of make her rate a quarter of the job every hour. And then Josie is a little different because she's doing it in 6 hours. So one job in 6 hours. So if we divided 1 by 6, well, that's just 1/6. So her rate is 1/6 of the job per hour. And so that kind of shows us there what we have to go with into solving the problem, which we'll do next. So we basically are going to be combining a fourth and a sixth, where each of them are going to be multiplied by x, because the number of hours, like the hours right here, that's what they're asking. How long is the question they're asking? So it'll be a quarter of 1/4 the rate times the number of hours plus a sixth times the number of hours will equal one whole job. And that's what we're going to see next. So now going to our solutions page, we have, like I said before, Well, this is supposed to be a 1/6, and these are 1/6. So what this is supposed to say right here is that's supposed to be a 6, and this is supposed to be a 6. So that's something to keep in mind. And so we have 1/4 of the job times the number of hours plus a sixth of the job in a number of hours equals one job. So we would be solving this rational equation to figure out how many X hours they would take to do it together. And so now if we look at our solution, if we are doing x over 4 plus x over 6 equals 1, our common denominator of all of these denominators, including we can add in a denominator of 1 right here, and that would just give us a common denominator of 12. So we can multiply everything by 12 like we did in class yesterday, and then we would basically have 12x over 4, 12x over 6, and 12. Dividing that all out, we get 3x plus 2x is equal to 12, and 5x would equal 12, meaning that 2.4 hours would be our answer. Moving to our next type of problem is going to be our motion problems. So we can clear that all off and move to that now. So with motion problems, the main idea with motion is that everything is kind of going a certain amount of distance based on their speed times how long they've been going for, or speed or velocity, depending on what you're talking about. You can also do that as distance over rate equal to time. And you can even add a third option to this, where you can tell you basically have your distance divided by time could also be equal to your rate. And that would also be kind of the same idea. So that's something to keep in mind as well. Now let's see an example of using this motion idea in a problem. So in this problem, we have an airplane flying west, and we have a 20-mile-per-hour wind. So that 20-mile-per-hour wind is going to be important. So we will underline 20 miles per hour wind. So going west along with the wind, so with the wind, they're traveling 450 miles. That is happening in the same amount of time for a different plane, or the same plane actually, is going to fly east 300 miles against the wind. So if it wasn't for this wind, the plane would be flying at the same speed going east or west. But if you've ever been on a plane going back and forth east to west or vice versa, the time that your travel in the plane takes is going to be different depending on which direction you're going, whether you're coming home or going to your destination from there. And we're trying to find the speed of the plane in the air, because this plane itself is flying at the same speed, but they're just not able to go as far when they're flying against the wind. They're going 150 less miles per hour. So this is a little trickier. So let's take a look together at what the solution ends up being and the approach ends up being for this problem. So the approach is easiest if you make a table, in that we have the plane, the two situations, with wind and against wind. And then we have the distances they're flying, 450 and 300. And we have the distance and the rates next to it. So we have 20 miles per hour added to the wind, or we have 20 miles per hour taken away from the wind, causing the plane to go slower. And to get time, like we talked about earlier with those formulas, we were doing time is distance divided by rate. So we would take 450 divided by x plus 20. And so now we have a proportion over here to solve, and we can kind of just cross multiply. So a little bit on that. First, make sure you're putting parentheses around the expressions with more than one thing, because then when you cross multiply, like so, that is what's happening in this second step. And you can see the 450 times the x minus 20, and then 300 is x plus 20. And then you're just kind of multiplying everything out and solving, getting to an answer of 100 miles per hour as the speed of the plane if you take away the wind affecting it helping or hurting its speed in general. And that concludes our second example and the second type of application problem with rational equations. Thank you for watching.